You probably need to answer something on that as well.
That's your screen.
No, that's what I'm doing now.
Oh.
It's way over. You have to do this. Oh, you got it.
Yeah.
Cool. Yeah, we get started. Perfect. So, welcome to our presentation and thank you for coming. I'm Diarmuid with Liam and Edges, and we'll be talking about matrix models, lattice simulations, and M-theory. So, first of all, first and foremost, we would really like to say thank you to Diaz and everyone here for this opportunity, and particularly our supervisor, Professor Denjo O'Connor, and the coordinators, Drs. Atri Day and Saiki Koizumi. This has really been brilliant. Under Professor Denjo's supervision, we worked on creating an algorithm in Python to simulate the dynamics of the bosonic BFSS model. And we'll go through that broadly chronologically. I will talk about just a bit of background and the main basic version of the algorithm we used, and the lads will then expand on that. So, a bit of background, we are pushed for time, so the bare bones of M-theory. You may have heard of it as a unification of the 5 consistent versions of superstring theory through different symmetries, as well as combining it with 11-dimensional supergravity as another kind of separate limiting case of it. It's considered an excellent candidate for a unification of all fundamental forces, but it does have several open questions. Most notably that we don't have a complete formulation of it outside the bounds of perturbation theory, which is why we don't know what the M stands for. It has been suggested that it may be mystery, magic, or matrix, because that brings us to the BFSS model, which is a quantum mechanical matrix model. That arises totally naturally from type 2A string theory in the low energy limit. And in that context, it forms an effective description of a collection of D0 branes, where the matrices of this model, the degrees of freedom of the matrices represent the interactions between the branes. And in that model, in that limit, the model itself is even described by 11-dimensional supergravity. So it is conjectured that in the limit, as the matrix size, or the number of branes, increases, the BFSS model becomes equivalent to M-theory. So it is an excellent place to study, and to study the dynamics of M-theory in a somewhat simpler case. And we did that by discretization onto the lattice and simulation via the hybrid Monte Carlo algorithm. So the hybrid or Hamiltonian Monte Carlo is a Markov chain algorithm that generates a sequence of random samples, random points, that converges to a given distribution, which can be any function we choose. So if we want it to be a normal distribution, we can choose f appropriately, and we can see that a histogram of our chain converges to that probability distribution. In just the same way, we can choose any function and it will converge just the same. So it does that by iterating from each point based on Hamilton's equations, which we all know from classical mechanics, and we define it for use in this case. So we define the Hamiltonian, as we're familiar, as the kinetic energy. We'll get back to that momentum term in just a moment, plus some potential, plus an action in this case. And that action we define as that on the left. So that has the effect of turning our probability function that we've chosen into a potential. So it is much more likely for a particle under this Hamiltonian to be in a place with a high probability. It has a low potential in that place. So we then evolve from a given random point, or random for a hot start, the origin for a cold start of the algorithm, and we evolve from that point for some later time in the Hamiltonian dynamics. So, as we know, that would normally be deterministic in Hamiltonian dynamics. So it would move, the point would move along that curve of constant Hamiltonian. That's a very simple one, but it could be anything, as we saw numerically. But that momentum is completely computational. It doesn't correspond to any physical value, anything really. We choose it randomly at the start of every iteration. as you can see here. So that gives us just a slight kick off that Hamiltonian, meaning that the next point will then be slightly removed from the Hamiltonian again. And we use that to propose a new point in phase space, which we accept or reject into the final Markov chain based on the metropolis check, which has the effect of comparing the Hamiltonian of the proposed point and the beginning point. And if the new one is far more likely, it is very likely to be accepted into the check. If the new point is far less likely, then it is very unlikely to be accepted, but it still can be. So we explore all of the phase space with a sampling rate proportional to the probability distribution that we have chosen. So we move through the phase space. We move through the phase space, iterate until eventually we have that lovely looking spread there, which you can imagine if we collapse that down onto just the x-axis and we take our histogram, then that would converge to a normal distribution in this case, or any function that we have chosen for our action. So we can then use that to compute observables because we have that chain. You could compute an observable against that distribution analytically, doing the integral, but you may not be able to. And in this case, because our chain of samples is already given by that distribution, we can just calculate the mean of our observable of each of those values. So that turns it into a much more manageable sum across our list. And we chose this model because it compares very well to random walk, Monte Carlo and all that. There's very low correlation between the points, but also because we can plug in any action we like to simulate any real system we like. So if we want to model a harmonic oscillator, we can plug in the Hamiltonian for a harmonic oscillator, and we can then calculate any observables of that we like. We can plug in any number of dimensions we like, and this is where it really comes into its own, because you definitely may not be able to calculate that integral by hand. We just sample more momenta that, just the same as in one dimension, wash away because we understand the distribution that we've chosen. And then we can even add more degrees of freedom. Instead of choosing a one-dimensional scalar for our dimensions, we can choose a matrix that we may interpret as with the degrees of freedom representing interactions between branes. Once we choose an appropriate action, we can then add yet more degrees of freedom. And once the action that we have defined can accommodate these degrees of freedom, we can simulate it just the same. So if we introduce a list of matrices at each step in the iteration, we can interpret them as progressions through time. So each successive matrix being some time interval, some discrete time interval moved on from the one before, and we can then simulate the dynamics, the evolution of this path as determined by any action we've chosen. Any action that does include the BFSS model that we introduced earlier. So to discuss more details of that, I'll leave you with Liam and Edges.
Thank you. So as we kind of saw in the beginning, the action is pretty important. It's kind of what we're studying. Actually, that's the distribution, the target distribution that we're trying to recreate. So I'm going to go kind of through the path integral formulation of quantum mechanics and sort of give a suggestion of why we're really concerned with the action. And I hope it's not too bad to follow. We start with classical probability, right? So if, let's say I take a measurement at A and I get the value A, I take a measurement at C and I get the value C. I want to know the probability of going from A to B to C, but I'm not sure what B was. You have to sum up over it. Quantum mechanics is really similar, except we replace that with complex numbers, and then the probability is given by squaring that number. This is going to be taken as the sort of the fundamental equations, and we'll just sort of start trying to generalize that. So let's say we took a measurement at A, we got the value A, took a value at C, the value C, and then all the way up to K. Basically, we have to sum up between all the other things. So we have B, and then all D, all the way up to J has to be summed up, right? If we imagine that instead of A, B's, and C's, we took X1s, X2s, X3s, X4s. I'll go up there in a second. and they can correspond to like different times, right? We can build up essentially a path, right, through space-time, right? As the epsilons goes to zero, more or less makes a path. And if we imagine that the variables are now continuous instead of discrete, right, we can replace those sums, as you see with these integrals. And then we can just define a region R as between all the A's and B's. I'm going to just go up real quick on the board and just show you what that looks like. Oh, yeah, sure.
You're told to use that. It's not be
Oh, yeah, it's perfect.
Can you hear me?
That's fine.
Is it fine with that?
Yeah.
I think it's been nice.
There should be a sticker there.
So, yeah, so this just sort of looks like this. If this is X, and this is, let's okay. This is X and T. So we imagine we start taking, say, a point here. This is X1, another point here, another point here, another point here, and just start choosing them randomly. You can see how this forms a path, right? And then we define this like region R, say something like this, and we have, say, AI, A2, A3, all the way up. Same thing over here, B. And we call this region here R. You can imagine that we start integrating over all these free variables. And that defines the probability that there's a path, right? As we integrate over all paths, it gives the probability of a path in region R, and that becomes important. So I'm going to move on back to the... Okay. So that's basically that. So the first postulate is that we treat all the paths basically equal, right? So well, somewhat. The magnitude is going to be the same, but and it's going to be given by this. And the thing on the right actually here is the formal integral, and we run into this a lot actually while we work with it. So it's kind of good to know what it means. It's this basically infinite number of integrals, right? Over some functional. That's also that's functional little bits. And it becomes a functional basically as this becomes a continuous path. It starts out as just a function. Second postulate, this is the one I really want to focus on, right? Because this is where the action comes in. And it sort of feels like it comes in out of nowhere. And it's sort of brought in as an ansatz in the derivation I'm used to. But Dirac actually has a paper on it and he talks about it. But basically, the phase is proportional. The phase is basically proportional to the action, right? And the reason that's the case, I mean, you can kind of show that it's going to be true by taking this classical limit, and you basically get the action. You'll basically recover the Lagrangian in that classical limit, but that's not really what we're concerned about. We're just kind of concerned about the action. So we define the action by taking. So how do when we're back in the discrete world? I'm just going to talk. We take basically between the xi's, we take the classical action, and then we take the total action by summing that all up, right? And when we combine that, we get this expression, okay, which gives basically that complex number that represents the probability that we're in R, right, generalized to this form. And we have these A's in here, which is basically the normalization factor that I've split up. And they don't actually always have to be equal, right? If you can take imagine you took different time steps, you could have different normalization factors for those different steps. So the important part here is we have an exponential to a sum. So the exponential function connects multiplication and addition, and it allows us to basically factor the thing. But before we do that, we do want to split the region up into two parts, basically the past and the present, and we call some point, some time, tk, right, with a corresponding xk, some variable. And we imagine we integrate, I'm going to actually just go back to the books today, as we're going to see. We imagine we take the, where are the colors?
That is tough to see.
Yeah, so if we imagine we define here as tk, and we split the region up into a past and a future region, right? We integrate over these variables. All the path information is basically stored in this factor, right? If we integrate over all this, all the information is stored in this factor right? And so all the information you need to know about what's going to happen in the present is stored in whatever this factor is going to be. And then a similar idea is that this represents sort of an experiment you can take. It's called an ideal experiment of what is the probability that given the path has been in here, that it will be in there, right? So that's what we're seeing. Yeah. Okay. So,
No.
sorry.
This is why I didn't want you out of my horrible list of tabs.
All your emails are gone public.
Yeah.
Stop sharing.
Yeah.
Sorry, Dermot. Right, so we split it up. And I show that you can split it up into two factors here, right? And I think this is kind of the big aha moment, right? We define those two factors in a special way, where we integrate all over the lower dx's, right? The previous time and the future times. You see something that I think most of us should be familiar with, right? This is the inner products formulation, and I think that should give a kind of idea why we are concerned if we're making some kind of quantum mechanical model that the action is probably going to be kind of important. Even the classical action is very important. And so to see a much more complicated form of the action, I'm going to let it go to Edges.
Yeah, so I'm going to go through how this all comes together to the bosonic BFSS model. So taking that action that Diarmaid talked about at the beginning, we look at just the bosonic part. We do a Wick rotation to Euclidean time. You end up with this, where this upper limit beta is just 1 over Boltzmann constant times the thermodynamic temperature. And these xi are just n by n matrices, with n being the number of degrees of freedom. And this dt here is the covariant derivative, which accounts for changes in the gauge field of the system. And the gauge fields themselves are just the representations of fundamental forces for our system. So I'm going to look more at that covariant derivative, because the aim is to take that integral and transform that into something that we can actually write an algorithm with. So we discretize time to lambda sites with the spacing given by A is equal to beta over lambda. And we impose a periodic boundary condition that the initial point has the same conditions as the final point. And then looking at the time derivative part of the covariant derivative, we have this, which is just a definition of the derivative. But then to maintain gauge invariance, we want to actually transport the field at the next point back to the current point on the lattice. And we use unitary transformations for that, of these unitary matrices here. And then we have the full covariant derivative. So then taking this here, turning that into summation, squaring it out and putting this in, you get a bunch of terms that end up, you can group them together in the end, and you get this fun action here. But we can further simplify that by getting rid of these u's as much as we can. So we do this change where we redefine like x goes to x prime, and then x prime is the first transformation and so on. We also define this w, which is just a long list of these transformations. And then doing that, again, rewrite the bosonic action to look like this. Then we do more, where we decompose W into V, D, V dagger, where V is a unitary matrix, and D is given by the diagonal. A diagonal matrix where the elements are e to the I theta, theta being angles associated with the unitary transformation. But then, again, we choose a gauge, so that in the end, we get this nice long bosonic action. And this is actually what we used in our algorithm. But then that's not the only action we're interested in, because essentially what we did was changing coordinates, and there's an extra term that pops out from that due to just the way that the transporter and gauge fields interact. And we essentially get this extra phase term, where again, these theta are angles associated with the unitary transformations. And we will add that to our Hamiltonian as well. So in the end, this is our Hamiltonian for the system. So here we have the PINs and PLDs are canonical momenta corresponding to the Hermitian matrices XIN and the angles theta L. And you remember Diarmaid said we chose just a random XIN, which also now in this case that is a list of lambda matrices that are all n by n dimensional. But then we chose random momenta and also random angles. And then we do that check that Diarmaid talked about to see are these relatively likely. But then to actually do the Hamiltonian dynamics, we need the forces on the system. We just use Hamilton equations for that. And performing those derivatives, we get all of these very fun equations. They look very complicated, but this is basically what we plugged in to look at the dynamics of the system.
What does this notation mean? This 0 ml and ml?
So the ml refers to the angles, the thetas. 0 meaning, so this subscript here is the point on the time discretized lattice. So this 0 means the very first one. N here goes from 1 to lambda minus 2, and this is just the second to last point on lattice. The reason we have to split it up like that is because of things like the periodic boundary condition. You can't do the transformation. It gets a bit messy there at the end. But then, so that's what we were able to use in our algorithm. But to check if our code actually makes any sense, we want to have some sort of check to see, does this agree with what we'd expect analytically? Well, we could use the partition function, which encodes the statistical properties of the system to do this. So we have this partition function. Then we define this ZB, where there's this extra B term, and it's just a dummy variable that later we set to B1. Then we do change variables. We take the derivative with respect to B, and after rearranging a bunch, we get the expectation value of the action is equal to n squared lambda over 2. Remember, n is the degrees of freedom, lambda is the number of lattice points that we have. And then this is what we actually got. So this blue horizontal line here is the value I just talked about there. That's the expectation value that we got analytically. And then this is what we actually simulated. So you see initially the action starts off, the expectation value of the action starts off very high, and it decreases, then it begins to oscillate around a point. Unfortunately for us, that is what we got analytically. So it looks like our algorithm agrees with what is expected. There's a second check we could do with Wigner's semicircle law, which is to see, do our matrices behave as expected after we do everything? And basically that's saying, if we let X be a symmetric n by n matrix, where the entries are independent and identically distributed random variables with bounded moments, then the eigenvalue distribution of X should look like a semicircle in the high n limit. Now, I couldn't go too high in the ends just because my computer couldn't handle it, but you can see here there is a semicircular looking distribution. So that is a great sign that, again, our code is working as we would expect it to. I think that was 150, because I think that took me like 2 hours to run. So now it wasn't that powerful, so I was like, I'll leave it there. But typically, when you look up the semicircle law, they'll use values of n that are like 1,000, 10,000, and so on. And it's quite computationally intense. But yeah, so that's basically it. We wrote that algorithm. We checked that it works with what we expect analytically. If we had more time, we would have added fermionic interactions to our model. And the infinite n limit of such theory is conjectured to be a formulation of non-perturbative M theory. Unfortunately, we didn't have time for that. But yeah, our algorithm with that modification could then be used to study the low energy limit of the BFSS model. And that's it's basically our project. And we'll take any questions if anyone has any. Thank you.
Why is that semicircle expected?
That's basically just the semicircle law for these are the prerequisites. And it just happens for our system that obeys what we have. So we weren't getting that semicircle. There'd be something weird going on with the eigenvalues, which would correspond to like energies in our system.
That comes from just random matrix theory. That's not particular to the BFSS model or anything. That's just purely numerically that would have been expected.
For non-commutative variables, the Wigner semicircle is the equivalent of the Gaussian distribution for commutative variables. What it means is that and the way it arises is if you have a Gaussian distribution which has a unitary symmetry and you diagonalize the matrices, the eigenvalues you can show are distributed according to that semicircle law. I could derive it on the board for you, but it comes from removing the unitary symmetry. And when you average over the unitary symmetry, it has the effect of giving something universal. So you expect
So it's like it's an actual statement like which can be proved.
It's a theorem, yeah, there's no question. It originated with Wigner. It originated with Wigner in nuclear physics, where he was talking about. He was interested in understanding the excited states of nuclei. And if you think of a nucleus as made up of protons and neutrons, and you're thinking, well, I've got this condensed object here, and it's made the matrix elements of the Hamiltonian. Well, it can make transitions between all of these different states, and it's pretty random. So he modeled it in terms of a random matrix, and it agrees quite well with aspects of nuclear physics. So that's the origin of the problem. And then Friedrich Dyson generalized it to some mathematical results in random matrix theory. It then gets people who use it to find properties of number theory, conjectures associated with the Riemann hypothesis. It goes off in various different directions in that side. And it's used in physics and mathematics. And if you've got a random number of antenna and they're sending signals, you can check that it roughly it can be transformed into a matrix, and each signal is transforming. You can make your antenna into vector space. The signals that they're getting are acting as endomorphisms of that vector space, and then if they're random, you get to Wigner semicircle, and you can use it to check certain properties of those things.
What happens to Gauss's law? Is it taken care of?
Gauss's law was implemented by the gauge field.
So, I mean, if you compute the expectation value of the Gauss's law in this way, it automatically comes up to the zero.
Gauss's law is a constraint.
Yeah.
And the constraint is implemented by the fact that they put in that they had a gauge field. If you go back to your action, the BFSS one.
This one?
Even before that, just because he's asking about Gauss law, it's more obscure there. In this one, for instance, there's a covariant derivative with respect to t. That involves a gauge field. That gauge field is non-dynamical because there's no momentum conjugate to it in the Hamiltonian formulation. So it's a constraint. And that constraint is Gauss's law. So integrating over that gauge field implements Gauss's law. That is the integral in the lattice theory. That is the integral over the thetas that they're doing. Those integrals implement Gauss's law.
Yeah, I think what I'm asking that this is theoretically supposed to be the case, but since this thing is being done numerically,
Yeah.
I mean, how well is it being taken care of?
Excellently. It depends on whether it's as good as any other part of the theory, right?
Gauss's law is a statement about the Hamiltonian. This is not the Hamiltonian. This is the path-angular formulation of the problem. So the Gauss's law here appears as the integral over the holonomies. I don't think it is the question should be posed here. It's not a Hamiltonian formulation. When you write it in.
Gauss's law is a constraint, and the constraint is coming from the integration over the thetas in this case. If you just skip forward,
That is what is left over, yeah.
in the end, these thetas that you can go into the next one, the integral over the theta L and theta M there, that implements the constraint. If you do it precisely, it implements the constraint precisely.
One more question: how many time steps do you have?
Lattice points, do you mean? For this here, this is just 5. But we tried, basically we ran at different times. I think the most I went up to was 30, but it gets very computationally intense once you start going up.
So here you use this Markov-Chain Monte Carlo integration. So means like, is there any numerical error? Like if you will start with other set of random points,
Oh,
will be your result? Like how much is?
well, that's kind of what
deviation?
we're relying on, that randomness.
Yeah, so that's why I'm asking. Like if you start with other set of random points, means and they will also converge.
Yeah.
Time.
And that was handled in the thermalization because, depending on where you start, it takes a while to find the region of phase space that is particularly likely. So we discarded the first few points that it took to converge to that.
The graph there shows it nicely. If you start, you've started up in some configuration which looks like it's a high temperature state, and it has cooled down in the dynamics. If you relax onto this, if you started somewhere else, if you started at 0, for instance, it would rise up to that. So the late time is the one that washes out that early stage of the thermalization that you mentioned.
The changes would be just this, the height of this, and maybe the shape in general. But if it's working correctly, which it was for different tests, it would still oscillate around a value.
Do you have any other plots of this kind that you can show?
Not that I can show. No, they're not in the slides.
So your steps are defined, or you just use when it will converge, we will take that result like that, or you just know that okay, we will iterate in that many steps and we will see what is.
Yeah. Well, so say we plot this, we might see, okay, if I was to try and take the number here, that's not really a good estimate. But so we do a plot like this, and then we say, okay, now starting here, we might find the mean of all the values here, and we'll take that as average.
Because whatever I know in this Markov's and Monte Carlo method, so they just try to start with different points, and they just try to converge everything. And after they used 200, 300 iterations, and with 200, 300 and maybe more a different set, and then so that if the majority is converged in that point, then they took that point as a okay, this is our final result. It's with only one set, it's not, I don't know, only with one set and one plot, you can say that, okay, it's my actual result.
Oh, we did do that.
So
I just have this here to demonstrate the behavior, but we did it for different combinations of these, different number of total iterations, and we'd get this behavior every time for the same values, unless, of course, that blue line would change depending on what these are.
So it's pretty well, Hamiltonian Monte Carlo is pretty well understood, and there's a whole part about error analysis. But the reason it's preferable over random walk suggestions and proposals is because it converges really quickly. And there's a whole I could show you if you're interested in the paper on actually trying to figure out what the errors are. But it's you can do some analysis on it, and it's decently defined, I think.
Yes, of course. In any of these things, you can't make any statement without doing error analysis, and they haven't. There wasn't really time to go into
I think the most confusing part about this is that we constantly mention the Hamiltonian stuff. There's no actual Hamiltonian involved in the physics. We're just using it as a way to generate proposals, right? Because we understand that Hamiltonians tend to stay constant, right? So if we do some sort of Hamiltonian evolution with whatever our random variables are, we're going to more or less keep this number constant. And if that probability is a function of that number, we'll be able to keep the probability constant. So we're able to go through these probability contours through the distribution, and then slowly build up the distribution as we move up and down the probabilities. That's sort of the main way it converges. And because it moves around the distribution really quickly, you're able to get a lot of proposals that are really far away. That random walk would be sort of stuck here. You're just able to get to the other vacuums, I guess. So.
Can you repeat my question again? So when we are working in real time, that is in Gauss-Christic method, then the way this conflict will appear is I'll have something like e to the I, A naught, then some combination, and then when I path integrate, I get delta of that combination, which will be both the constant. But now one is working with imaginary time since one is in thermal, so I don't have that I.
You do.
I do.
Yes. Because each of the I, A naught is a group element. It's a unitary. If A naught is a matrix, then if it's an n by n matrix, then that's a unitary matrix. So each of the I, A naught is the unitary matrix that they have diagonalized to get the thetas. So the I never disappears. It's because it's not. It's constrained.
Now I.
If there's no other question, we can just.
You mentioned low energy phenomena. What exactly are you looking for that?
What do you mean? Sorry, could you?
Specifically, you said you study the low energy behavior of it.
Yeah.
That classification, what do you mean by that?
No, just because it's conjectured that in the low energy limit, it's hypothesized to be described by supergravity. So if you took an algorithm like ours, you had the fermionic interactions, and you wanted to study supergravity, you might be able to use our algorithm to do that, as long as that beta doesn't get too high.
You require large n as well for the
Yeah.
quantum for the supergravity. It's in the large n limit that you get supergravity. If you don't have large n and you go to small beta, you're expecting to have full n theory corrections relevant to it.
Am I right to say that we would hope to see like Hawking radiation in it? Is that the Hawking temperature? That's what we're sort of seeing if it matches up to.
Well, I mean, that's another story which you didn't get into. Is there is a dual gravity formulation of this, and the beta of this would be the Hawking temperature of the dual gravity. But that you can see Hawking radiation in a Euclidean setup. No, you can't.
I think we can go to the next talk and we can discuss later if anybody has some extra questions. Okay.
Okay, so thanks everyone for coming today. My name is Killian Kelly. This is Rob Kelly. Introduce yourself, I guess, but yeah. So we're going to start first and foremost by, of course, thanking some people. So we want to thank our supervisor, Dr.
Of course.
Yeah, exactly. Yeah, exactly. Twins. We'd like to thank Dr. Salkme Mondal, who supervised this project. He taught us a lot of physics and helped us with problems that arose. And he was really patient with us, so thanks so much to him. He was a wonderful supervisor. We want to thank Dr. Achude and Dr. Sakikoyumi for organizing the weekly meetings, keeping us on track, keeping everything running smoothly and correcting our work. You guys put a lot of effort in. So I think I can speak for everyone. We really appreciate it. And finally, the Dublin Institute of Advanced Study here. Thank you so much for having us come and take on these research projects. I learned so much stuff, probably more than I expected I would learn. And it's just been such a wonderful time. So thanks to everyone who was involved in the internships this year. Okay, so I'm going to get started. So our title is on chaos and string theoretic black holes. I'm going to begin by giving you somewhat historical introduction to try to motivate why you would want to study chaos in black holes, and then I will sort of define how we quantify chaos in classical systems, and then Robert is going to discuss the actual system that we've studied here. So I'll start at the very bottom with here we go. So with what is a black hole? So in classical physics, a black hole is just a region of space-time where the gravitational field is so strong that nothing, not even light, can escape. Black holes are actually older than general relativity, so the idea of black holes came about in the late 1700s. People started already to think about objects whose escape velocity could exceed light, and so they would be dark, and so hence they called them dark stars, I think, at the time. But in Einstein's theory of general relativity, we described them with the Schwarzschild metric shown here. So this is a spherically symmetric solution to Einstein's field equations, and it describes the space-time geometry of the black hole. You might have heard Denjo mention earlier that this surface at O equals 2m is not actually a real singularity. It's specific to the coordinate system you choose, but In a certain quantum system, you could say that the surface of RCM is the event horizon of the black hole. So this signifies the point of no return. So once a particle crosses the event horizon, no matter how much energy it has available to it, it will be pulled towards the real singularity at the center of the black hole, and it will never be able to escape the gravitational field. So that's classical physics. In quantum physics, the story gets a little bit more interesting. So in 1972, Jacob Bekenstein wrote a paper where he proposed that black holes should have entropy, and his argument was basically that you could take a system or a particle with some entropy and throw it into the black hole, and the entropy would be somehow lost to the black hole. So he wanted to protect the second law of thermodynamics, which is wise policy. So he suggested black holes should have an entropy, and furthermore, he suggested the entropy should be proportional to the area of the event horizon of the black hole. Then 2 years later, in 1974, Stephen Hawking studied quantum effects in space-time around a black hole, and he found that black holes are actually thermal systems, so they radiate energy continuously, and they have some non-zero temperature known as the Hawking temperature. And furthermore, he was able to provide a precise formula for the entropy of a black hole. It's shown here. And the key physical feature would be the entropy of the black hole is proportional to the area of the event horizon, just as Bekenstein said it should be. So this is great. The trouble is, with most thermal systems, we have some statistical interpretation for the entropy. So we can think of the entropy as arising due to there being many microscopic configurations, which all give rise to the same macroscopic thermodynamic properties. However, for black holes, the statistical interpretation of the entropy was not very clear. And so this is where string theory enters into the picture. So string theory, as I'm sure we all know, is a candidate for a quantum theory of gravity. And so because of this, it should be able to describe black holes. So it made some progress in the direction of statistical origins of the entropy of a black hole. When in 1994, 2 guys, Andrew Strominger and Kumtum Dafa, used objects in string theory known as D-branes. A D-brane is an extended membrane in string theory, and they originate by imposing Dirichlet boundary conditions on the endpoints of open strings. And Strominger and Dafa were able to superimpose these D-branes together to come up with a system which shared similar properties to those of black holes. And furthermore, along with this, there was a certain degeneracy which they could use to provide statistical interpretation of entropy. And miraculously, they were able to reproduce the Bekenstein-Hawking entropy of a black hole for a special class of 5-dimensional extremal black holes in string theory. So this was a big win for string theory, and it was good progress towards statistical origin of the Bekenstein-Hawking entropy. So this is why string theory is relevant in our descriptions of black holes. So where does chaos come into the picture? Well, thermal behavior is very closely related to the idea of chaos. So thermal systems are said to be ergodic. And this means that if you choose a point in phase space of the system and follow its trajectory through phase space, if you leave it for sufficiently long, then you'll see that the phase space trajectory will visit all points in phase space. So it will efficiently explore all of phase space. And this ergodic nature comes about due to the exponential divergence of trajectories in phase space. And the exponential divergence of nearby trajectories in phase space is one of the defining characteristics of a chaotic system. So there's this link between thermal systems and chaos. And as we know, black holes now are thermal systems, so it's natural to ask if black holes exhibit chaotic behavior. And it turns out that they do. So there's been recent work done in quantum information theory, which has led to a paper by Douglas Stanford, Stephen Schenker, and Juan Maldacena. And in this paper, they conjecture an upper bound on how chaotic a system in nature can be. So this is the bound they propose. On the left-hand side, you have what's known as a Lyapunov exponent. I'm going to sort of discuss how you would arrive at computing a Lyapunov exponent in the next slide. Before that, for now, you can just think of it as being a parameter that quantifies how chaotic a system is. So it quantifies how fast chaos sets in a system. And they propose that for all systems in nature, the Lyapunov exponents must be less than or equal to 2 pi times k Boltzmann over h bar times the temperature of the system. Furthermore, they found that black holes actually saturate this bound. So not only are black holes chaotic, they are the most chaotic, they're maximally chaotic, they're the most chaotic systems in nature. So this provides, I think, ample motivation for us to take on this project and to study chaos in black hole systems. So now I'm going to just talk about how we quantify chaos in classical systems in general. So before we choose points in phase space to study the chaos of, I want to just mention this idea of thermalization. So to thermalize the system, what we'll do is we don't want our point that we choose x0 to be associated with the initial conditions that we chose. So we'll take a point in phase space and evolve the system then forward in time for sufficiently long such that the phase space trajectory explores ideally all of, but a good chunk at least of the phase space, so that we end up with a point in phase space which is sort of uncorrelated with the initial conditions that we ourselves chose. So the system somewhat forgets the initial conditions that we had chosen, and now we have a point in phase space, which I'm going to call call x sub 0, which is the point in the thermalized system. So what we're going to do now is perturb this point slightly to obtain a new point. And when I say perturb, I just mean, so in the system, it'll come down to essentially adding some small perturbation term, there's some small distortion term to the Lagrangian, simulating the system for a small amount of time just to obtain a new nearby point in phase space. Then once we have this point now, we can study the trajectories of these 2 points in phase space over time. So Hamilton's equations tell us how to evolve time forward. And we can define a metric on phase space, which I've just written sort of qualitatively here. So this delta big X of t will be the distance between the 2 points in phase space at some later time. And of course, this is our initial point at some later time, which we can call the reference configuration, if you like. And this is the perturbed system we can call the perturbed configuration. And they're just labels. It doesn't matter which one's which. The point is we have 2 nearby points in phase space, and we can study their trajectories. So now we can ask, how does this quantity here evolve over time? And for a chaotic system, we expect the behavior to be exponential, to grow exponentially over time. So we see that the distance at a later time between the 2 points should be at the order of the initial distance times some exponential growth. And you see here we have the old Lyapunov exponent that we've seen. So this is where these show up. And so that they quantify sort of the rate of growth of this quantity here. So there's one more thing that I want to mention, which I will write for. Do you want to take the stop sharing?
So could you still say that your system is perturbative?
Perturbative?
If the expansion is growing exponentially.
For finite perturbations, for a finite change, and for compact phase space, this behavior that you saw, the exponential behavior, is actually not true for all time. So if we look at the distance at a later time divided by the initial distance, and we look at it against time, then we'll see this exponential growth initially. But for compact phase space, this distance cannot get any larger than the total size of the system. So we're going to have to see this thing saturate to some parameter, which I'm just going to call n squared for now. If the system is a fast scrambler, which, I should say that the time it takes for the system this distance to saturate to its value is what we're going to define as the scrambling time for this classical system. So it's a classical analogy for the scrambling time, and we'll call it T star. And for a fast scrambler, which is just a synonym basically for a highly chaotic system, we should see that the scrambling time should be of the order of the logarithm of this parameter that the distance saturates to. So with this, and the other slide, which so this here.
Yep.
Okay. So with this equation here and this that I've shown on the board should be, I think, sufficient to understand our results here. So I'll let Robert now talk about the system and the results.
Yep, thank you very much, Killian. So I'm Robert Kelly, and I'm going to talk about the system we analysed and the results we obtained. So we're under the model of string theory, so we need 9 spatial coordinates to quantify an object in space. So if we have one D0 brane, that's 9 position coordinates. But if we have 2 D0 branes, we'll need 18 spatial coordinates plus 2 extra coordinates per spatial dimension to quantify the coupling between the 2 D0 branes. Because you can have a string starting on one D0 brane and ending on the second, or starting on the second and ending on the first. So in order to mathematically write this out, we would have a 2x2 matrix for every spatial dimension. And if we had n D0 branes, we would then have n by n spatial position matrices. But this is a model that represents the dynamics of these D0 branes. So we need the Lagrangian, which is here. We have a kinetic term here and a potential term here. And there's extra terms that I haven't written down because they are quantum mechanical in nature. And we're taking the classical approximation where these extra terms go to 0. So you can also see that there's a G term which quantifies the coupling of these D0 branes. And there's also this capital D subscript T term, which is the covariant derivative that brings into play the gauge field of the system. So it's just a partial derivative with respect to time, and then minus the commutator with respect to some gauge field A subscript t. But we're not really dealing with the change in the gauge field or anything, so we're just going to set the gauge field equal to 0, and this covariant derivative becomes the velocity. And then now we're going to take the classical approximation, and to do that we have to set the weak coupling and high temperature limit. For all of our simulations, we'll be in this weak coupling high temperature limit, and this simplifies the Lagrangian to what I showed earlier, and we can get the equations of motion. So here is the equation to find the acceleration of the system, and with that we can get the dynamics. And then on the right, since we set the gauge field equal to 0, we have this Gauss's law constraint that has to be constrained as the system evolves in time. But so we have one state, one thermalized set of coordinates, but we need two very similar states. Both of the states have to have the same total energy. They have to be very close together, and they have to also be able to be evolved into from the Lagrangian. So they have to, the constraints of this system have to be conserved from getting both of the two states. So in order to do that, we define a second Lagrangian, which is going to be the perturbation Lagrangian, and we get it by just adding a new perturbation term into the original Lagrangian. And to ensure that the perturbation between the two states is very small, we set these coefficients, these CK terms, to be sampled from the normal distribution with mean of 0 and standard deviation of 10 to the minus 8. So they're going to be very small, and they're going to be random also. And then from this Lagrangian, we can get new equations of motion. So these are perturbation equations of motion, I'll call them. There's an extra term here in red. And then in order to get our two states, we have a thermalized set of coordinates. We then evolve the thermalized set of coordinates with the original equations of motion to get state x1. And then we go back to the thermalized coordinates. We then evolve the thermalized coordinates with our perturbation equations of motion to get state x2. These would be very similar because those CK coefficients were very small, but they won't be exactly the same. So there will be a little distance in between them. And then we can evolve both of those states simultaneously while measuring the distance between them for 100 seconds. And the distance we've defined as this metric here, so this delta x of t term, is just the square root of the sum of the squares of the each spatial dimension of the two states here and there. And this is what we did for every single simulation we ran. And how would we find the Lyapunov exponent? Or how would we find that the system is chaotic? Well, if you recall this equation that Kilian has introduced before, if you take the logarithm of both sides, we expect this delta x of t term to be linear, the logarithm of delta x of t to be linear with time. And also, in order to find the Lyapunov exponent, we would just solve the above equation and get an equation of a very familiar form. It's mx equals y. So we would expect the Lyapunov exponent to be the slope of a plot of this logarithm against time. So this is the basic analysis we've done. So to go into some of the results we found. So we've simulated we've done 6 n equals 4 simulations with different total energies for each simulation. And we found this shows the 6 data sets, each in a different color. And you'll find that, well, the y-axis of this plot is on a log scale, and this delta x of t against time begins linearly on this log scale, so it is chaotic in nature. It does follow that equation I had on the board before, and you'll see that it also, the distance increases up to the maximum distance that Kilian has talked about before. And even when we change energy from, say, 63 up to 1,890, this maximum distance is not really dependent on the energy of the system. And now we can try and find the Lyapunov exponents. So just plot this logarithm against time. And we find these for the exact same data sets. And we see that, well, the Lyapunov exponent is the slope of each of these data sets. And we can see that the slope of each data set increases as we increase the energy. of the system. So there is a correlation between the Lyapunov exponent and the energy of the simulation we ran. So we take the linear fit of those 6 data sets, and we find the Lyapunov exponents, and then we're going to just see what energy dependence these Lyapunov exponents seem to have. And this is the plot of the Lyapunov exponents with energy. So they do indeed appear to have an energy dependence, and we found that the Lyapunov exponent roughly is proportional to e to the power of 0.24 for the n equals 4 case. And then we've repeated all of this for the n equals 7 case, and we've got a very similar looking plot. And we got the Lyapunov exponent is proportional to e to the power of 0.22. And the actual equations for those curves of best fit are shown here. So there's errors involved, and these 2 equations for the n equals 4 and n equals 7 case, they don't agree with each other within the experimental error I've shown here, but also the errors I've shown are an understatement because they're only errors on the curves of best fit, assuming those data points had no errors involved in them. But we have been running numerical simulations, so there are definitely errors involved in those data points. So it is still, the errors involved here will be greater than I've represented them. But at least to leading order, the Lyapunov exponent scales roughly the same, no matter what, even when we changed n, the energy dependence on the Lyapunov exponent didn't seem to depend on n. So at least to lead in order here. So we're come to a conclusion that the number of D0 branes in the system, which is what n represents, does not really change the Lyapunov exponent too much, it appears. So, and this is also, this e to the power of 0.24 also obeys a conjecture we found that any chaotic system, the Lyapunov exponent is proportional to e to the power of c, where c is less than or equal to 1. So our system obeys this conjecture as well. And now we've also gotten different Lyapunov exponents and compared them with other literature values. So from Schenker and Gurari and Hanada, their paper, they found this relationship for the Lyapunov exponent. And we've basically run our own simulations with g squared n equal to 1 and t equal to 1, just to simplify this equation. And we found good agreement with other literature values. So moving on to how Killian was talking about the possibility of this system being a fast scrambler. And the definition of a fast scrambler here is the scrambling time scales as log of n squared.
I just have one question in the previous slide.
Yeah.
What was G in your calculations?
For us, it was G was 1 over the square root of n.
Sorry?
G was 1 over the square root of n for our simulations. So then G squared n equals
that. That G squared n term was cancelled.
Yes.
And what was the temperature for n equals 4 and 7?
For the n equals 4 and 7, the temperature depends on the energy that we made. So if the energy, so let's say for the n equals 4 case here, we have the energy is 63, that corresponds to a temperature of 1.
Okay.
So the temperature would increase as we increase the energy of these systems for the n equals 4 and n equals 7 case.
What is the definition of the energy exactly? I mean, how do you define the energy of the system? I mean,
it's the kinetic energy plus the potential energy. So if we go back to the Lagrangian, we had the original Lagrangian we had here, we had the kinetic energy minus potential energy, but for the total energy of the system.
You take the sum, and so you take that term and you compute it.
Yeah.
How do you compute? You just compute it?
Yeah, so we've
expectation value or?
We have the literal position. So we set initial position matrices and set initial velocity matrices and then simulate the evolution of that for a particular time step. So we're taking a numerical integration of it to find the actual position and velocity and acceleration matrices for every time step in the future. So for every time step, we're able to find the actual total energy of the system, because we have to.
It should be conserved, or is it?
Yes, it was conserved.
It is conserved, yes.
To 7 significant figures, it was, because of taking numerical approximations.
So it's a kind of a molecular dynamic iteration, and the energy is conserved over that. Trajectory.
Over the entire simulation in time. But okay, we were moving on.
How do you measure temperature here now? So the temperature is simply given, or is it?
Yeah, we use the equipartition theorem to get an equation of temperature in terms of the total energy of the system. So it's in terms of the total energy equals 3/4 by the degrees of freedom by the temperature. So we can find the degrees of freedom. It just scales as the number of the zero branes in the system. So then we can link the total energy and the temperature to that. And so if we want to, because it has been found that Killian mentioned that black holes are fast scramblers, we want to see if our system of the zero branes retains the fast scrambling nature of chaotic systems. So in order to find that the zero brane system is fast scrambling, we just have to see that the scrambling time, which is the time it takes for the system to saturate, for the distance between the two states that we're simulating to saturate, that changes, that scales as log n squared when we change the number of the zero branes that we're simulating. So also we have to note that the scrambling time is the time it takes for this maximum distance to arrive. And since it's a linear plot, so the distance scales linearly with respect to time. If we're taking the log, then, and the Lyapunov exponent is the slope of that graph, that if you change the slope of a linear plot, then, so if you increase the slope of a linear plot, then the time it takes to reach the maximum value will decrease. So there's an inverse dependence between the scrambling time and the Lyapunov exponent. And also, since we found that to lead it ordered, the Lyapunov exponent doesn't depend on n, we can simply plug in the Lyapunov exponent into this scaling equation. And then we multiply both sides by the Lyapunov exponent and take the exponential of both sides. And we have this e to the lambda L by the scrambling time. And this, if you remember from the equation that governs chaotic systems, scales the exact same as this delta x of t. So now we find that for fast scramblers, the delta x of t, k is any constant. We don't know where the Lagrangian chooses the k of the system, but for a fast scrambler system, for any k here, well, if the system obeys this for any k, then it is a fast scrambler. So we find the delta x of t at the scrambling time for many different n's, and we should find that there should be some k where this delta x of t at the scrambling time divided by n to the power of k equals a constant. So in order to do that, we did 3 different simulations with n to the power of 8, n equal to 8, 12, and 16. And we found empirically that for this system, k equals 1/2. So then we plotted delta x of t over the square root of n. And hopefully we'll see that it's a constant as the system becomes maximally diverged. And here's the graph here for the n equals to 8, and n equals to 12, and n equals to 16, and they all converge to the exact same point as the scrambling time is reached for each of these simulations. So we found then that that condition, that the delta x of t at the scrambling time divided by the square root of n does equal a constant, no matter what n you choose. So then the system of the zero branes is a fast scrambler, so it does retain that property from a black hole. And then just to summarize the points we've made, there appears to be this energy dependence on the Lyapunov exponents. We've haven't had time to find this energy dependence for different ends and to do error analysis to see if this energy dependence does actually change when you change n, but at least to leading order, these equations are similar enough that we can still clear that. And also we found good agreement with previous literature values for the Lyapunov exponent. And finally, we found that the system is a fast scrambler as we would expect for it to be able to simulate a black hole. These are the main results that we found in studying the system. So thank you very much for this. Are there any questions?
Yeah, you said the cutoff point was n squared, but there was parts in the graph where the cutoff points were different.
Yeah.
Earlier, what's that about?
So you'll notice that the energy dependence might have a very small dependence on n, but to the leading order of the Lyapunov exponent, that small dependence doesn't truly matter, but it's true that these different maximum values that the distance gets to are different for the.
About it's saturating at different times.
I think it's the other slide.
Okay. Oh, sorry, I'm going with this one.
Yeah, that one.
Oh,
exactly.
So the problem here is I've divided all of them by the initial distance between the two simulations, this delta x at 0. And for all the simulations I've ran, you see that the initial distance is different for them. And that's because we've picked random, the CKs were random, those coefficients were random, so the distances had to be random as well. So in this plot, the actual maximum value that these take doesn't really matter. Doesn't have any significance.
Yeah, it's just the slope. It's the important parameter.
Yeah, the slope gives the Lyapunov exponent.
The value k equal half is the value relevant for black holes. Is that what you're saying?
For this system,
yeah.
For this Lagrangian, it does appear to be yes.
So it is a fast scrambler because it is maximally chaotic, or is it fast scrambler because I'm not sure what is the relation between fast scrambling and
it's basically
black holes
fast scramblers are the most chaotic systems, but the fastest scramblers. So it's pretty much synonym.
And
black holes are the fastest scramblers we know of in nature.
Okay.
Yeah.
And fast scrambling means that the behavior is given by the value k equal 1/2. That's what it means, or it means something else.
Well, for this classical system, yeah, but scrambling time isn't really that well defined in classical systems. It's more of a quantum thing. But we basically made the classical analogy from quantum scrambling time over to here. So for a quantum system, basically it's a fast scrambler. For a quantum system, you can have a large number of n qubits, and you can find a small perturbation by just like flipping one of the qubits initially and seeing how that effect spreads out to the rest of the system. And then you can find like the Neumann entropy and complete the Neumann entropy, and when that reaches the maximum, that initial perturbation has saturated sort of spread across the system, and the time it takes should be logarithmic to the number of qubits squared. So and numerically we find this half, which can lead us to show that the scrambling time scales as log n squared, which would be a classical analogy of a fast scrambler.
Could you go back to the graph that was
is it this one? Or?
How did you choose these energy values? They seem a bit random.
Yeah, they do seem random here, but if you do it in terms of temperature, this is for the n equals 4 case, so E equals 63 corresponds to temperature equal to 1, and then E equals 630 corresponds to temperature equal to 10. And so this is like E equals to 315 corresponds to temperature equal to 5. And so they're all multiples of temperature. They're a lot neater when you do it in terms of temperature. I think we went up to temperature equals to 30.
Did you write code to about the system yourselves?
Yeah.
Yes.
What algorithm did you use?
Oh, yes. We used the velocity Verlet algorithm. I have a slide here. So in order to find the position at the next time step, delta x of t plus delta t, we can do it in terms of the position matrix before, the velocity matrix before, and the acceleration matrix before. And then once we have this position matrix at delta x of t plus delta t, we can now find the new acceleration using the equation of motion. So we can now find the new acceleration at t plus delta t and sub that into here to find the new velocity at t plus delta t. And now that we have position, velocity, and acceleration, we can just find the next step onwards after that. So we just did that. For delta t, we used 10 to the minus 4 seconds, and we simulated for 100 seconds. 10 million iterations.
How long will it take?
It depends hugely on the number of d0 brains. So for n equals 4, for 100 seconds, it was probably like 5 minutes. No.
Yeah,
10 minutes.
It depends on optimizations and things that you use. But I mean, I did for n equals 16. It took probably like 14 hours or something like this. I don't know, a long time.
Yeah, I think
It was in Python.
No, we have to learn C++ because it was Python was far too slow.
Yeah, in Python, would have taken days. So we just use C++. And
By any chance the code is available in GitHub?
we have the code, yeah, if you want it.
It's not there in GitHub or like
Yeah, we have it on
another.
Yeah,
We have it on GitHub.
I'm not sure if the repository is public, but we can show it to you.
Yeah, we can link the repository. Yeah. And then, yeah. It's a bit messy code.
It's nice.
You can put it in GitHub. Like you can clean
Okay,
clean code and you can put it.
it'll take a lot of editing. Oh, no, not yet. It'll be. And then,
Any other questions?
Well, yeah, in the beginning you said it supports all the points in base space. Does that mean the Hamiltonian changes, or is the Hamiltonian the same for the whole base space?
Yeah. So Hamiltonian is conserved throughout the simulation.
yeah, so it's all puts in phase space with the same Hamiltonian, with the same energy.
Okay. And that free then creates the whole space, or is the GPU?
Yeah, that's all of the configurations of the system that we can possibly evolve into is all points in the phase space with the same energy.
Okay, then we can next talk
Okay.
and then speak again.
All right. Good morning. Hello, everyone. My name is Keem, and this is Tom. And we're under supervision of Dr. Gian Domenico Palumbo. And our project is called Beyond Dirac Fermions. And before we get started, I would just like to thank everyone at IAS, especially our coordinators, Dr. Patrick Day and Dr. Saki Kozumi, for their patience and their support as well. And our project supervisor, Gian, has been absolutely instrumental throughout our investigations on this report. And I do wish he was here in person so that he could answer our questions. he's online. But yeah, anyway, I'm glad to share what our investigation and see what we have concluded. So, briefly, sorry. Okay, see it now? Yeah, I'm sorry, just I do hate the top bar.
change the screen to the actual tab instead of the whole screen.
There we go. There we go. Just mind the so we just
Not
took-
sure what the tab.
yeah.
You can just share your full screen, then I think.
Yeah, you probably just need to share it in a slightly different way if you do.
So, guys, there.
If you stop sharing it, reshare.
Yeah, I think you can stop sharing.
Okay.
And then reshare your whole screen.
Almost out of the window. So just the screen. Rather this screen, yeah.
Just share the file itself, not the screen. Just go back. If you stop sharing for 1 second. How you want to share, it should give you some options. Where's the file that you're sharing?
Yeah, that's the PDF there, that one.
Just the PDF, share the PDF. Share that. Click on, no, just click. You share the entire screen again.
No.
Just share that file. When you want to share, that's what it is. Just share that. It's an apple or something.
Was,
You have your laptop.
I can try my laptop.
Yeah, you can just.
I don't know if the battery will last on it. Me too. Sorry about this, guys.
That's fine.
So, allow me to reintroduce myself. My name is Hakeem, and I'm Tom, and we're under the supervision of Dr. Giandomenico Palumbo. And before we get started, I'd like to re-thank everyone again at DIAS, especially our coordinators, Dr. Atrie and Dr. Saki Koizumi, for their patience and their support. But most importantly, our project supervisor, Jan, who's been absolutely instrumental in our current investigation of the project itself, even though he hasn't actually physically been here that much, but his presence is definitely there in terms of his contribution to our project. So we would like to thank him. This project would not be possible without him. So before we get started, I'd just like an outline of the table of contents as presented. The first, we'll just go through some motivation for the project itself, and especially with the current paper that pretty much kickstarted the entire investigation for this project. And then we'll go into a brief overview of the Dirac theory in 3+1 dimensions, which is the relevant parts, at least, to our investigation. Then we will move on to our actual model, the Dirac-like model in 3+1 dimensions. And then we'll swiftly move on to the results, which takes up a significant portion of our presentation. We have multiple results for different cases. And then we'll go on to summary and conclusion. And then to finalize everything, we have to undergo investigation into further study based on what we discovered during our investigation. So for the motivation of the project, of course, Dirac fermions play a fundamental role, an essential role in both particle physics and condensed matter physics. The natural arena for our investigation is condensed matter physics, which is a specialization of our coordinator, Jan. And in quantum field theory, fermions can be categorized in three types, which are Dirac, Majorana, and Weil. And in condensed matter systems, especially solid-state physics, you have emergent quasi-particle excitations, fermionic types, which can be, as well as their associated phenomena, can be observed in high energy physics. In condensed matter systems, for instance, if you take low energy condensed matter systems such as graphene, the emergent quasi-particle excitations would be categorized as Dirac fermions. And then continuing on, there could be the emergent quasi-particle types would be Majorana fermions in superconductor heterostructures. So if I were to give perhaps an explicit case of the Majorana fermions, the uses of them as emergent quasi-particle excitations would be the topological protection of quantum information. So if you were to consider perhaps a toy model, a theoretical model, which incorporates a one-dimensional fermionic chain called the Kitaev chain, which is infinite in the bulk with a superconducting gap. In the topological phase, you would have exponentially localized zero energy states. You consider a substitution of the Majorana basis into the Kitaev Hamiltonian, it would lead to non-local fermionic states, which would make the system robust against local decoherence quantum interference, which has some potential use in topological quantum computing, with the associated reference to demonstrates the explicit experimental case of a one-dimensional quantum wire in a superconductor, which yielded zero Majorana modes. But the second point is perhaps the investigation that sparked this entire project, which was the quasi-particles in conventional crystals, because the emergent quasi-particles that were to be discovered in these condensed matter systems were exotic fermion types, which lied outside of the three classifications of fermions in the quantum field theory, because in condensed matter systems, there is a key distinction between relativistic fermions and fermions in condensed matter systems. Fermions in condensed matter systems are not constrained by Poincare symmetry, which is the full symmetry of special relativity, but rather they would be constrained by the crystal symmetries of the 230 space groups of the three-dimensional lattices, which imposes less restriction on the variety that these emergent quasi-particle fermion types can actually be. So they can lie outside of the three classifications of the fermion types in quantum field theory. And then based on the band topology of these emergent quasi-particle exotic types, there could be emergence of some fascinating surface states such as Fermi arcs, characteristic ARPEs or angle resolved photoemission spectroscopy signatures, as well as analyzing the magnetotransport properties of many material candidates, especially whose exotic fermions would be close to the Fermi level. And in figure 1, you would have some explicitly shows an energy dispersion near a threefold degeneracy of these exotic fermion types in this paper, which is listed at the bottom of the slide, which is perhaps the most instrumental paper of the entire project. It's what it is based on, essentially. And figure A would describe the form of the energy dispersion relations that we were managed to obtain in this investigation. And moving on, I'd like to discuss perhaps a general brief overview of the Dirac theory in 3+1 dimensions. The Dirac theory in 3+1 dimensions can be described by the following Hamiltonian, where psi is an n-component spinor, where n is equal to 4 in 3+1 dimensions, with the density Hamiltonian can be written as the following, where m is just the mass of a Dirac fermion, pi is the components of a momenta, and alpha mu are matrices, which would be referred to as the Dirac matrices that satisfy the following Clifford algebra, which is characterized by this anti-commutation relation, where delta mu is the Kronecker delta and I is the identity matrix. Moving on, I'd just like to give some general property. After this slide, we can prove that the alpha matrices can be even order matrices, dimension 2s by 2s, where s can be some positive integer. In 3+1 dimensions, the value of s is 2, leading to a 4-dimensional matrices. And using these matrices, which are associated with the momenta and the mass term, we can construct the density Hamiltonian, and upon diagonalization of that Hamiltonian would yield the following eigenvalues, in which the eigenvalues can be known as your standard relativistic energy momentum relations. And then the superscript J just denotes the degeneracy of your corresponding eigenvalues, which is equal to 2 in 3 plus 1 dimensions. And moving on, just like to give some properties of these alpha and beta alpha matrices, which would pose some relevance in our investigation of the Dirac-like fermions, which would be the exotic fermion types. First step is we require, due to the fact that we're trying to construct Hamiltonians, they would ensure that the alpha matrices are of course remission, square matrices that yield eigenvalues plus or minus 1, constant matrices that don't depend on position or time, and they satisfy the following anti-commutation relations, which is characteristic of the anti-commutation relation that's associated with the Clifford algebra that is required by the Dirac matrices. And the trace of these matrices are 0, and thus using conditions 2, 3, and 6, we can show that alpha matrices are indeed even order matrices. It's evidence in 3 plus 1 dimensions, lowest value of S is 2. And if you're, initially one is tempted to consider the Pauli spin matrices because they satisfy all the above conditions and they're 2 by 2 matrices. So perhaps they might be useful in some construction of some 2 by 2 representation. But unfortunately, they are unable to construct, for instance, alpha naught corresponding to the mass term in the 2 by 2 representation. So the next available representation where we'll be able to construct all of the momenta as well as the mass term to yield the eigenvalues corresponding to the relativistic energy momentum expression. The next lowest available representation would be 4 by 4, in which we show that S is equal to 2 in 3 plus 1 dimensions. So alpha matrices are 4 by 4 Dirac matrices that satisfy the following Clifford algebra. And the 4 by 4 representation is also known as Pauli-Dirac. And you can decompose the resulting density Hamiltonian into these to explicitly show these alpha matrices corresponding to each component of the momenta as well as the mass term, where the 0 underline is the 2 by 2 zero matrix, 1 is the 2 by 2 identity, and then of course the Dirac spinner is just a 4-component spinner in 3 plus 1 dimensions. And my colleague Tom will just take over to explain the model of our proposed Dirac-like theory.
Right, so we begin in a similar way to what we started with for the Dirac theory by postulating a form for the Hamiltonian. It'll take the same form as in the Dirac case with psi and n component spinner again, except n in this case can take the value of any natural number rather than just the even natural numbers for the Dirac case. We continue then on by postulating the form of the Hamiltonian density, which, like similar to Dirac, should be linear in the momentum and mass terms, and this time we have to construct these beta matrices rather than the alpha ones, with the addition of this fifth beta matrix that corresponds to a second mass that will be independent from the first mass. An important point to note is that these beta matrices that we're going to construct should not satisfy the Clifford algebra, because the alpha matrices that we showed for the Dirac case, they actually generate the Clifford algebra. So if our beta matrices also satisfy the Clifford algebra, then we're just back to the Dirac case. Okay, so the Hamiltonian that we're going to construct should have the following eigenvalues, the same shape as those for Dirac. This middle one is simply the relativistic energy dispersion. This second eigenvalue on the right hand side is same shape as this one, except corresponding to the second mass. But because we're going to be dealing with beta matrices that have dimension 5, 6, 7, and 8, we have to consider the possibility for an odd number of eigenvalues. Now, each of these square root eigenvalues will come in pairs, one for the positive and one for the negative. So in order to get an odd number of eigenvalues, we have to include this zero eigenvalue. Now, a consequence of this zero eigenvalue is that it makes our theory not Lorentz invariant, because according to special relativity, there can't be, if you have a particle that has mass, unless it's tachyonic mass, in which case it's a complex number, but we'll not go there, you can't have a zero energy. So consequence is our theory will not be Lorentz invariant. And that's not bad news as such, because this non-Lorentz invariant property will mean that our beta matrices won't satisfy the Clifford algebra as we need. So another set of matrices that will prove important later on in the results are these 3 by 3 Gell-Mann matrices. There's actually a set of 8 of them, but we only needed to steal 4 for this case. They were originally developed by Gelman to model the quark model and the strong interaction. We'll not be using it for anything like that. They just have a nice shape. And if we form the Hamiltonian density down here, using these 4 matrices, we get the correct shape of eigenvalues. So that sparked our interest and thought maybe they could be useful for constructing beta matrices of higher dimension. And importantly, these do not satisfy the Clifford algebra as well.
Is that why you chose these specific matrices?
Out of the 8 Gelman, yes. Yeah. Okay, so the model that we're going to develop is going to follow, or it should follow, SO3 symmetry. So the wave functions that correspond to our particles will be on 3 dimensions rather than 4-dimensional space-time like the Dirac. And that's because, again, our theory will not be relativistic, so they will be rotations in 3 spatial dimensions. The Lie algebra for SO3 is this vector space defined here, and it's simply the set of all n by n matrices that satisfy these 2 conditions. The sum of the matrix and its transpose gives a 0 matrix, and the trace of all the matrices has to be 0. And the generators for this algebra, or the basis vectors for this vector space, have to obey this commutation relation. And what's interesting is that if you set n equal to 2 in here for SO3, what you get is the generators are actually the Pauli matrices, so the set of 2 by 2 Pauli matrices. And we know that the Pauli matrices represent particles that spin half, which begs the question that the dimension of these generators corresponds in some way to the spin of the particle, and it's actually by this relation here. Now, we did calculate the generators for each dimension of the beta matrices we're going to calculate, but I can guarantee by the end of the presentation you'll not want to see another 12 matrices, so we've excluded them from the presentation, but if you're really interested, they're in the report. Okay, so wrapping all that up, we have the goals of the project outlined here. Number 1 is to construct a set of n by n matrices, beta mu, or n between 5 and 8, that will construct a corresponding Hamiltonian density that has the correct Dirac-like eigenvalues. Then we will plot these energy dispersions on a graph so that we can see them looking all beautiful. And then finally, what we're also going to do is we're going to try and find a 6th beta matrix, beta 6, that corresponds to the additional 3rd independent mass, which is very exciting. So I'll hand over back to Keem here to discuss the start of the results.
Thank you. And so we come to our first result for the 5x5 case. And the 5x5 case was by far the most problematic case out of all of the cases that we encountered. Because just to provide some brief context to our methods, which we excluded from this presentation because the results actually took up the majority of it. Initially, we tried to, our very first method was trying to utilize characteristic polynomial and then trying to determine the coefficients, but that proved way too taxing by hand, and trying to find some general form simply was not feasible. So then we moved on to, up at that point, we knew that, okay, what kind of density Hamiltonians actually generate the eigenvalues that we wanted, and there were 2 cases which were the Gelman. There's density Hamiltonians which were generated by the Gelman matrices, as well as the Pauli-Dirac, but it's not necessarily Pauli-Dirac since that satisfies the Clifford algebra, but we can utilize some of the elements and try to modify them in order to construct terms that would give us our desired Dirac-like eigenvalues. And so in this case, case was first proposed by Jian actually just to show that it is possible to build multiple mass terms in the 5x5 case, which we managed to do before, but we initially discarded because we ended up with these mass terms right here. So how do I? Yeah, so we end up with these additional mass terms, and our Dirac-like model required that the mass terms are independent. So initially, we discard them, but Jian proposed that we impose this condition. If we group the mass terms with sufficient free parameters, the sum of the squares of these masses can lead to which will lead to effectively an independent mass m squared, such that we can simplify our obtained eigenvalues into this form right here, which is the correct form that our Dirac-like model needed. So it satisfies everything.
I have one question.
Yeah.
Like, what does these independent masses mean? Like, doesn't seem to be any energy, like any kinetic energy associated to these masses. Because you just have one px square, one py square, and one pz square.
Yes.
There's no index to that.
So by increasing of the mass, by adding additional independent mass terms, you can add additional dispersion relations in the once you plot the real spectra. It adds to additional from the experiment. But there's no, we haven't given any initial value of px, py, pz squared, but we can have the ability to control or fine tune the values of these masses, so we can change the deviation of the bands in our real spectra, the distance between them. So it's just a matter of showing that it is possible in the sense, but that's all right.
Sorry, maybe I missed it. What is M2, M3? What is M3, M4, and M5?
Oh, they're just free parameters, essentially, because the problem is that we were using in the 5x5 case, we were unable to decouple, for example, M1 and M2 from each other. So we just added, okay, why not add additional mass terms and then group them all together into this. In this case, we're
this M3 to M5, they're like inside this beta matrices?
If you decompose the resultant Hamiltonian matrix into the beta matrices, you just they would be part of the beta matrices, but they're just free parameters essentially. They're not actual mass terms. But for the purposes, we can just for concise purposes and for we can just group them up into this single independent, which effectively acts as an independent mass, such that these eigenvalues here, M1 and M2, would be effectively independent from each other, thus satisfying our Dirac-like model, if that makes sense.
Since there's a rotational symmetry between M2, M3, M4, M5, can't you just turn off M3, M4, M5 and have just M2 and achieve the same result?
Yes.
Yeah, I think that would work.
Yeah, it would work, but just to show it is possible to build additional mass, you can. But yes, certainly you can remove these mass terms as well. But the initial idea was that we had this term, but initially we thought perhaps it's wrong because we didn't think it would be. We wanted to be independent, but we didn't realize you could impose this trick to just group the masses into an independent mass term. So that's why. But just because the direct sum approach that we had was the only method that where we were able to actually decouple a mass M1 from M2, for instance. But this is not a direct sum approach because it doesn't work for the 5x5 case. So in this case, we did come across an unexpected result while investigating the 5x5 case. We managed to construct a Hamiltonian that yielded eigenvalues corresponding to a real spectra of energy dispersion relations, but the Hamiltonian that we constructed is not Hermitian, and which was quite an interesting case to consider. So that prompted a venture into non-Hermitian quantum mechanics, and according to a paper that was outlined in 2001 by Mustafa Zadeh, titled Pseudo-Hermiticity versus PT parity time symmetry, he referred to non-Hermitian Hamiltonians with a real spectrum as pseudo-Hermitian. So in this case, we just obtained the pseudo-Hermitian matrix as an example for the 5x5 case. And by rearranging, we can rearrange the terms as well as interchange the momentum and the mass terms, and we end up with many additional matrix configurations that yielded eigenvalues that satisfied our Dirac-like model for the 5x5 case.
So this non-Hermitian case does have what's the word? Sorry?
Real eigenvalue?
Real eigenvalue, but yeah, I mean, you can find a basis in which it is Hermitian.
But in this case, it's...
Oh, you mean that one, like?
Sorry, it's not possible to find a base on me. Can you hear me?
Yeah.
No, sorry. I wanted to say that no, it's not possible. This is purely non-Hermitian. You cannot find any basis such that that you remove the non-Hermitian part. This is called pseudo-Hermitian quantum mechanics, which completely support real spectra, and is completely different from standard quantum mechanics. But still, you still get this kind of Dirac-like dispersion.
If you construct the eigenvectors corresponding to these eigenvalues, they are not orthogonal, is it?
We only considered the case for the eigenvalues because we're only interested in the spectra at that point. So we haven't actually considered taking the eigen spectrum to get the eigenvectors. We only considered the eigenvalues.
I thought it's eigenvector.
Yeah, in terms of the eigenvectors, you get a different answer because the eigenvector of H are different from eigenvector H dagger. So you have to distinguish H and H dagger as two independent different Hamiltonians, just because it's not Hermitian. But this is not a problem because you can implement B-orthogonality condition. You can normalize everything. But at the end, you can generalize really, you know, all the result that works for standard quantum mechanics can easily generalize to this pseudo-Hermitian regime. The unitary evolution is real. Sorry, it's unitary. So the system evolves unitarily because the spectrum is completely real. I think this is also an important point.
Just to clarify, Jen, are these eigenvalues or singular values?
These are all the possible eigenvalues of this Hamiltonian.
They're not singular values, they're the eigenvalues.
Yeah, these are all the possible eigenvalues. They are all real. There are no imaginary or complex eigenvalues. All of them are real.
And then what are the singular values then?
Sorry, I didn't get it, sorry, the audio is not good. Can you say again?
The eigenvalues, so you're not diagonalizing the matrix.
The matrix, no, this matrix has a pseudo-Hermitian symmetry. So it's possible to show that this Hamiltonian is related to H dagger through a transformation that is called the pseudo-Hermitian transformation.
I'm just curious to know if they're the eigenvalues of the singular values. You said they're the eigenvalues, so they're not the matrix is not diagonalized.
The matrix, no, well, you can diagonalize, no, you can, these are all the, well, this is the diagonals, well, you can diagonalize, 16 is the diagonalization of 15.
So they're the singular values?
Yeah, it's in their mission.
Unitary matrices that are different on either side.
Yeah, again, yeah, the difference is that H is different from H dagger. They are different. So if you diagonalize, yeah, but the spectrum are real. So they have the same spectra, but they have different eigenvectors.
Okay.
H and H dagger.
And moving on, just the we plotted the eigenvalues corresponding to the real spectra of the energy dispersion relations for the 5x5 pseudo-Hermitian case. Incorporating a side view as well, just to explicitly show that they don't touch. Using standard notation, crystal lines of K for energy dispersion relations. And we obtained, for example, the 6x6 case for the resultant Hamiltonian. And this was the very first result that we got for the 6x6 because we knew that there were 3x3 density Hamiltonians constructed from the Gelman matrices gave the correct Dirac-like eigenvalues that we needed. And this yields these beta matrices, which from this relation with the direct sum, where 0, 3 is just a 3x3 zero matrix. And this is the explicit form of the matrix for the 6x6 density Hamiltonian and not compatible with the Clifford algebra due to the nature of the Gelman matrices themselves, which are used to construct this density Hamiltonian. And there's another example that we got for the 6x6 case, not using the direct sum approach with the Gelman, but it utilized the terms. Each term usually corresponds to either a mass term or a momentum term with an associated imaginary part, because once you undergo the calculation, you'll end up with the elimination of cross terms that would otherwise end up in your eigenvalues. And then by imposing the same condition of grouping the mass terms with sufficient free parameters, we obtained an independent mass term, which we can then use. That is Yeah, this one's a bit of a typo actually. There should be M1 and M. This M prime because we imposed a different matrix that had two constraints, but this one had one. So this was an oversight that we forgot to rectify in that case. So sorry about that. But it should be M1 and a capital M. And these are distinct eigenvalues that have different independent mass terms and thus satisfying our Dirac-like model in this case. And then, of course, simplifying it into the expressions with the superscript denoting the degeneracy. M1 and M2, this is just general, corresponding to our first case with the direct sum of the Gell-Mann density Hamiltonians, and then the plotting of the dispersion and a real spectra of the energy dispersion relations, where M1 is not equal to M2, so there's some separation between these bands right here, because if we set M1 equals to M2, they just converge and it just looks like a single. And then explicitly, just a side view, just to show that they don't touch. And now my colleague Tom will just take over for the 7x7 and the 8x8 case.
Okay, so for the 7x7 case, we initially followed a similar procedure as the first 6x6 case that you saw. And we want to construct a 7x7, so we took the direct sum of the 3x3 and the 4x4 matrices. The form of the beta matrices in this dimension is given in equation 22. And then the matrix form of the Hamiltonian density is the same. So this top left-hand side, 3x3, corresponds to the Gell-Mann Hamiltonian. And then the bottom 4x4 is just the Hamiltonian that corresponds to the Dirac's theory. We get the eigenvalues of this, and that's what we obtained there, simplified, and the dispersion relation as well, where we can see the gap between the bands. So they're not touching, and again we've set M1 and M2 not equal so that we can see the separation between the two paraboloids, and that's for n equals 7. Another case for n equals 7 that we obtained was using this parameterization method by adding M3, 4, and 5. Again, same story, we can set big M squared equal to that sum of squares and replace with M squared in the eigenvalues to obtain the correct dispersion. And finally, for n equals 8, in this case we were able to, because of the size of the matrix, it was easy enough to include the third mass term with beta 6 in the Hamiltonian. This is the form of the Hamiltonian density with the addition of this beta 6 M3. And then again, the Hamiltonian density in its matrix form. The eigenvalues of that are shown here. And again, what we can do is group M3, 4, and 5 together, regard them as parameters that we can use to tune big M so that it is independent from M1 and M2. And we obtain the correct dispersions for these eigenvalues and the zero as well. Okay, and finally, just to show the plots again for those dispersions, we can see 3 levels for the paraboloids. This corresponds to the 3 masses, and again, they're not touching in between. Okay.
So just for me to briefly review this, just regarding the summary and the conclusion. Back in methods, we talked about the initial goals of our project, which the first goal was to construct n by n beta matrices that once we used to construct the resulting density Hamiltonian will yield the desired Dirac-like eigenvalues that we wanted. And we constructed numerous density Hamiltonians for each n case from n by n case from n between 5 and 8. Unfortunately, it's not feasible to include every single matrix that we had. If we did, this presentation would easily exceed 50 slides, perhaps. So perhaps you could check them in the report for a huge number of matrix configurations that we did manage to get for each case. But for instance, the ones that we mentioned were just general ones, like for instance, the one that we didn't use for the non-direct sum, you can just move the mass terms around and the different matrix elements and just swap the momenta and the masses, and you still end up with the same eigenvalues, but it still means a different matrix configuration in the end. And so we found density Hamiltonians, n by n density Hamiltonians for each case, and we were in the progress of trying to construct a general method that we could use to apply to each case n between 5 and 8, which account, well, I didn't include it in this presentation, but you could check it in the report because it only accounted for the 0 eigenvalue and 1 eigenvalue corresponding to 1 independent mass, but the second independent mass was still a bit arbitrary in comparison for specific to each n case. But it only worked between 5 and 8. Once I tried it between n is equal to 9 or 10, then it kind of broke down. So there's some progress to be made there, but about 66% is not bad, I would say. Additionally, our goal was also to obtain a matrix beta 6 that's associated with a third mass term, which we managed to do for the 8x8 case. The only case, in fact, it was perhaps the only case that was large enough to accommodate enough mass terms such that we can differentiate the 3 independent masses, M1, M2, and M3, and then using parameterization method, we can just set M3 equal to capital M. And then Hamiltonians with 0 eigenvalues are not Lorentz invariant, and the algebra that's associated with them still needs to be discovered. Only suitable for describing low energy systems such as condensed matter systems because they don't have a high energy counterpart. For instance, in the case where I was talking about the unconventional exotic fermion types in the conventional crystals, they're not constrained by the Poincare symmetry of special relativity, only the crystal symmetry to 230 space groups, so that essentially diversifies the type of fermions they can actually be, but no high energy counterpart because they're not Lorentz invariant. And now, colleague Tom will just talk about further study that we'd like to achieve based on our investigation.
So possible avenues for further study in this investigation would be to, first of all, calculate the anti-commutators for beta. So for the Dirac case, the anti-commutators were just given by the generator for the Clifford algebra. In this case, they won't be the same, of course, because ours will not generate Clifford algebra. And of course, they should be anti-commutators rather than commutators because we're trying to describe fermions. And the fermionic statistics are described by the anti-commutator. Second point that we can investigate is this non-Hermitian Hamiltonian that we discovered for the first 5x5 case. Unfortunately, we only discovered it last week, so we didn't really have as much time as we would like to sort of get a better understanding of this non-Hermitian quantum mechanics. But at first glance, it seems very interesting. Basically, what they do is they take the condition for the Hamiltonian to be Hermitian, throw that out the window, and replace it with this condition on the wave functions to say that they have to obey these particular parity and time symmetries, and if they do, then the spectrum of the Hamiltonian will be real. So that would be a very interesting avenue for further verification. And finally, another possibility we could consider is restricting the momentum components to 2 or 1 spatial dimensions. The reason we could consider this is because much of the research currently operating for Majorana fermions consists in sort of 2x2 dimension, two-dimensional planes or one-dimensional lines. And what happens is that can breed a sort of new genre of statistics. So in 3 spatial dimensions, we can only have 2 possible statistics available to us, and those are the fermionic and bosonic statistics. But whenever we restrict the spatial dimensions, we can obtain non-abelian statistics, which basically means that whenever you make a switch of particles, the order in which you perform that switch actually matters. And this ordering is actually the source of the potential for using Majorana fermions to encode information, quantum information. So considering this could lead to a possible discovery of more interesting statistics for these Dirac-like fermions. Thank you for listening.
You didn't check the anti-commutators for the beta matrices that you constructed?
So for, I think there's one set of them I have in the report, but at least that I can see, it's not very easy to compact them into a nice form. So it would kind of look like a bit of a mess on the board of commutators for each of them.
Okay, so you don't know like what kind of algebra is like?
No.
And you then also do not know if for different cases the algebra is same
as Clifford, or for the different dimensions.
Yeah.
No. But I wouldn't imagine it would be.
because especially for the third, the addition of the third mass, I wouldn't imagine there would be because of the addition of that sixth beta matrix would lead to sort of a more messy multiplication in the commutator than if that sixth beta matrix wasn't there, if you know what I mean. So the result of the commutation would be a matrix with fewer zero elements. You know what I mean? With the addition
It
of
can
that
still
sixth.
be the same algebra, right? They just.
Oh, right, okay. Well, possibly.
And other question is, how did you diagonalize your Hamiltonian?
Using Mathematica. So just a one-line command.
And it was just easy to do that with all the Hamiltonians.
Yeah, it took less than a second. It just spat it out.
Are there particle systems which are really described by this kind of considerations? I mean, you have just sacrificed quantum relativistic invariance, you have sacrificed hermeticity of quantum mechanics, Clifford algebra structure. I mean, what is it exactly that you are getting here?
So I think the sacrifice of the Lorentz invariance shouldn't be too much of a problem if we're sort of aiming to find these particles in condensed matter systems, because they're not going to be very high energy systems anyway. So it shouldn't have to satisfy relativistic postulates then. And what was the second?
The second one is much more important, quantum mechanics. I mean,
So I think
the fact that observables are emission, they have eigenvalues.
So that non-Hermitian is more of a generalization of quantum mechanics rather than a restriction of it.
It is not that it should be a generalization. I mean, it's not a generalization. I mean, it's
there was a paper that
from being straightforward.
I think which paper is it? Yeah, so that's reference 1. I think it's a review article that outlines sort of basic mathematical structure of the pseudo-Hermitian quantum mechanics rather than the Hermitian.
Maybe let me ask you. Suppose that this system describes some correspondence system. Presumably, that's an effective description of a particular situation, but that the underlying description is still quantum mechanical. Would you have any comments on how apparently non-Hermitian quantum mechanics might arise from an underlying Hermitian theory?
I mean, really, are there systems which are like that? I mean, this is very important. That's the motivation. If there is an actual system which is described by the non-Hermitian quantum mechanics.
Yeah, maybe I can give an answer to this. So all the quantum dissipative systems are not Hermitian. So once you introduce a thermal bath in an open quantum system, then you have a non-Hermitian Hamiltonian. So that is very common to deal with non-Hermitian gain and loss. So in this particular case, we are in a situation which there is gain and loss plus some symmetry that constrain the system to still be real in the spectrum. And so it's basically in quantum optics, in dissipative quantum mechanics, you find everywhere the non-Hermitian Hamiltonian. They're very common everywhere, experimentally speaking. I mean, whatever dissipation.
What you are speaking about here are open systems. They are not quasi-particle systems.
No, sure. No, but yeah, but even in an open quantum system, you can still define quasi-particles. So you can imagine now this pseudo-Hermitian Hamiltonian, which basically is a quantum system with some gain and loss, such that you still get your quasi-particles and plus this extra term that break their Hermitian condition. So this is completely well defined, and again, has been studied experimentally in many situations. So as I said before, all these dissipative systems, quantum optics is very common to deal with this. Quasi-particles are always well defined because we are not introducing interaction on this level. It's basically still a free fermion system plus some gain and loss, and naturally you get you break Hermitian condition.
What is the problem with the other higher dimensions, 9 and 10? I mean, seems to work well. Seems to work relatively well.
Yeah, we just didn't consider them. We just stopped at 8.
Right.
No.
I found it to be troubling really that Hamiltonian is not mentioned. It's very, I mean, I'm not comfortable with this personally, so that is an actual objection, not just a feeling.
Is it then more appropriate to work with density matrices rather than wave functions in this situation?
So, in the outline for the project, it was that we should work with the Hamiltonians or the Hamiltonian densities rather than the wave functions. So, that could investigating sort of structure of the wave functions as well would be another area that could be further investigated into.
Okay, maybe we thank everyone for their participation and especially Zaki and Archie for all the hard work. Ultimately, Zaki is ill and not able to be with us, so I see you're online, Zaki. Thanks again.
Thank you.
May I also thank all the summer students. I learned a lot from your project, and you all did brilliantly well. It was amazing.
It was great,
really
yeah. Excellent.
Yeah. Well done, all of you. Yeah.
And I'm going to stop the recording.
I think there's some tea and coffee arrangements.